Okay, so in this kinetic friction review question, it also combines a lot of Newton's laws and constant acceleration kinematics. We're looking at a 2 kilogram wooden block being launched up to a wooden ramp, inclined at a 35-degree angle. The block's initial speed is 10 meters per second. Coefficient of net friction is 0.2, and the coefficient of static friction is 0.5. How far along the incline does the block travel before coming to rest is the first question. And how fast is the block moving when it returns to its start point is the second question. So maybe we'll start with a sketch before we jump into some of the math. So I'll just use this space down here to draw a quick picture. So we've got a 35-degree angle, and then we've got a block, 2 kilogram block on that incline. Okay, so we've got this 2 kg block, and we know it's been launched up at 10 meters per second. And we're going to figure out how far along the incline does the block travel. So to determine this, so we're looking at displacement. Displacement will depend, of course, on speed, but once it's on an inclined surface, it's also going to have an acceleration. So not only due to the weight force, but due to the friction forces. So we're going to have to figure out what is the net force on the object to figure out its acceleration. Then, knowing that acceleration is going to be constant, we can use constant acceleration kinematics to figure out how far the block travels along the direction of the incline. So I'll also maybe here note that I'm going to apply a convention that my y direction is perpendicular to the incline, and my x direction, I'll assume that up the ramp is positive. Again, that's you can make that decision yourself. You can choose up the ramp to be negative, and you just need to keep track of your signs. So if we were to draw a Freebody diagram for this block, we know there is a weight force on the block that's straight downward. That's the weight force on the block by the earth. There is a normal force that's perpendicular to the ramp. So on the block by the ramp. And since the block is initially moving upward, at least for the first question, it's moving upward, and it's moving relative to the ramp, the kinetic friction force is down the incline. There's a friction force on the block by the ramp. And the sum of these forces will basically determine the net force on the object, and that will be linked, of course, to its acceleration. So if I choose, again, there's going to be no net force perpendicular to the ramp, so I'm only going to focus on the x direction, parallel to the ramp. And we can write the net force, we call that the x direction. The net force on the block in the x direction, there's going to be two forces that are going to be down the ramp. There's going to be the friction force down the ramp and the weight force down the ramp, and both of these are negative, so we're going to sum sort of two negative forces. So I'm going to have negative friction B, or plus a, sort of in a sense I'm adding two, so I'm just going to add these two negative signs. So these are both in the same direction and both of these forces, the component of the weight force, are pointing down the ramp. That's why I have these two negative signs. So minus the weight BEX. And then these are linked to, so the friction force is going to be minus mu k times n, and this is going to be minus mg sine theta. So that's the x component of the weight force that points parallel to the ramp. But the normal force is linked also to an mg quantity, so it's mg cosine theta minus mg sine theta. So we have a common term of mg sine theta in both here, so we can take this out. So the F net B in this x direction is going to be negative mg, and then we have mu k cosine theta minus sine theta. And if you plug all of this into your calculator, you will find that this net force is equal to, I believe, 14.5 newtons, but I'm going to go ahead and figure out the acceleration. So since the acceleration also depends on the mass, we sort of save ourselves a little bit of work if we try to determine the acceleration, and we can cancel these m's. So the acceleration for this, at least this first question, on this x direction, is going to be this net force, it's negative mg times the mu k cosine of theta minus sine theta, all divided by m, so it's F net over m, if you wonder where this equation comes from. So I'm dividing the net force by the mass, so this is where the masses will cancel. So the acceleration is negative g mu k, so it's a subscript there, cosine theta minus sine theta, and this should make sense that the acceleration will be negative, and this term in the parentheses should be a positive number, because as the block is moving up the incline, the acceleration should be down the incline, but both the net force points down the incline, so the acceleration should have a negative value. And so you have g is a constant, 9.8, at least when it goes to the surface of the Earth, 9.8 meters per second squared. Mu k is given here as 0.2. You have the angle of 35 degrees both in the cos theta and the sine theta. You put those into your calculator and you should end up here with negative 7.2 meters per second squared. So that's the acceleration of the block. So it's accelerating down the incline with an acceleration of negative 7.2 meters per second squared. So since the friction force and the weight force component are constant at all times, as the block is moving up the incline, it's a constant acceleration, so we can use constant acceleration kinematics to figure out how far along the incline the block travels before coming to rest. So if we consider the constant acceleration kinematics equations, so we know that the final speed squared equals the initial speed squared plus 2a delta x. Again, calling the x direction parallel to the incline. Here the Vf will be equal to 0. We're trying to figure out how far the block will before coming to rest. So I'm trying to figure out, we know the Vi is equal to 10. So again, it's launched up the incline, so this would be a positive 10. So I'm trying to figure out what is the delta x. So the delta x will be equal to negative Vi squared if you bring that across. Vf is 0 divided by divided by 2 times a. So that would be our negative times our 10 meters per second, all to be squared, divided by 2 times negative 7.2 meters per second, all to be squared. And this should work out to be 6.9 meters. And that's how far the block should, the block should travel almost 7 meters up the incline. Okay, so that should cover the first part of the question. And now we have to figure out how fast the block is moving when it returns to its starting point. So I'll do that on a separate piece of paper. So in the second part, what changes here is the direction of the friction force. So maybe as some additional work here, you could ask yourself the question, will the block even slide down the incline once it comes to rest? And we can do that by comparing the max static friction force to the weight force component that points down the ramp. If we just want to do some additional work here, so the weight Bex is equal to mg sine of theta. So if you plug that in, it's in 2 kg times 9.8 times the sine of 35. I believe that works out to be 11 newtons. And the Fs max is mu Sn, which is mu S mg cosine theta in this example. And that equals 8 newtons. So at all times, the weight force component down the ramp is bigger in magnitude than the max static friction. So the max static friction is not going to be large enough in order to keep the block at rest. So when the block becomes instantaneous rest at the top, it will begin to slide back down again because again max static. friction force is not large enough to keep it there at rest. So for the situation, for the how fast the block moving returns to its starting point, well, what you should know here is definitely not going to be 10. And once you know about energy, you'll see that as the block goes up the incline, energy is taken out of the system and converted to thermal energy on the way up and on the way down. So there's some transfer of initial kinetic energy to thermal energy, so the block should be moving slower when it returns to original point. So again, redrawing the Freebody diagram. Again, the weight is of course still present on the block. And there's a normal force. Again, so they're identical as the previous diagram. But what's interesting, the block is now sliding down the incline. So the friction force, this kinetic friction force opposes motion, so now the friction force is up the incline. So it's working in a sense the opposite direction to the weight force that is pointing down the ramp. So in this particular case, the net force on the block in the x direction is going to be a positive friction force minus this sort of weight force. So I'm kind of summing these two forces, so it'll be FB or minus the mg sine of theta. So if you work to this in a sense, this will work out to be again equal to mu k mg cosine theta minus the mg sine of theta. Again, the same type of values, but this again, in this particular case, we were adding the friction force to the weight force in the previous situation, or summing two negative numbers. But now we have a positive friction force up the ramp, and then we have this weight force down the ramp. The weight force down the ramp is more, again, has to be more dominant than this kinetic friction force. And if you plug in your these values, again, the mu k, the m, this friction force works out to be, I think, negative 8 newtons, but again, you could consider the acceleration divided by the mass. The acceleration of the block in the x direction will be that negative 8 newtons divided by the 2 kgs, or you can just divide this all by m, and this gives you negative 4 meters per second squared. So here we can see that the acceleration is definitely smaller than in the previous case. So in this first part of the question, the friction force and the weight force are working together, giving the block a greater acceleration down the ramp, where now the friction force is opposing the weight force, so there's a smaller net force, and therefore there is a smaller net acceleration. So again, working with constant acceleration kinematics, and this time we're thinking about the Vf squared equals Vi squared plus 2a delta x. So when it returns to a starting point, it will travel that 6.9 meters that we just determined from the previous question. So I want to figure out what is Vf. We know that Vi equals 0, so the block is going to start from rest during the sort of falling stage. So my Vf will be equal to the square root of 2 times a times delta x, where in this particular case I will have the 2 times the negative 4 meters per second squared. The displacement will be down the ramp, so it will be negative 6.9 meters. So the speed at the bottom of the ramp, this works out to be 7.5. So it'll be negative, so the square root will give you plus or minus 7.5, so this is moving down the incline. Negative 7.5 meters per second would be the final velocity, or 7.5 meters per second the final speed. And we can see that this is definitely smaller than the initial 10 meters per second for which the block was launched up the incline. And again, once you study energy, you'll see again this will make sense in that the block starts out at a certain amount of kinetic energy, and you can think about the transfers of thermal energy in the block surface and in the surface of the ramp, and there's a transfer of kinetic energy to thermal energy, so at the end the kinetic energy of the block will be smaller. But you can for this particular question, we're doing this from an entire analysis of Newton's laws and constant acceleration kinematics.